So we shall discuss in chapter 17 the basic distribution theory of the multivariate models. And then we will recall some of the concept that you learned in chapter 3. So if you have forgotten about chapter 3, just recall it, because all of the results for the univariate models in chapter 3 will be discussed as a multivariate model here in chapter 17. So relatively, chapter 3 results will be carried over as a multivariate case in chapter 17, specifically in sections 1 and 2. So if you're familiar with the chapter 3 results, you can easily relate it here. Okay, so let us just review some of the notations that we had. When you see a matrix A, this has components Aij. So Aij means it's the ijth element of the matrix A. The difference between a simple matrix and a random matrix, each of the entry in a random matrix are random variable. So when it is a random variable, it means that it will have its own distribution, no? And then the expected value of a random matrix will be defined as the expected value of each of the entries of your random matrix Xij. Covariance can be denoted by this symbol or simply the capital sigma. And it is actually a measure of relationship between the random vector Xij and the other random components in your matrix, the X prime J prime. So when we are talking about covariance of Xi and Xij, this is equivalent to the variance of X. Okay, so another term that will be often be seen in this discussion is the trace of a matrix. So the trace of a matrix is just the sum of the diagonal entries of your matrix, which is defined to be this symbol. The trace of A is the sum of all Aij. So the entries, or actually you can have the entries of A in the diagonal. Now A here is an n by n matrix. Okay, so these are some properties of your trace. So when you get the trace of the transpose of a matrix, it's still equal to the trace of the original matrix A. Next, the trace of A B transpose will be equal to the trace of B A transpose, where your A and B are M by N. So let me recall. Okay. So when I use this notation, this one, at least it's something here. When I use this notation, when we say X is an element of R and P, it means that your X here is an N by P matrix, no? So ang nasa ibabaw is the number of rows, and nasa ubos is the number of columns. So in this notation here, so both A and B here are M by N. So if we look at the conformity of this matrix, A is m by n and B prime will be n by m. So this matrix here, AB prime will be an m by m, no, matrix. Also here, B is m by n, so prime will be again n by m. So both AB prime and BA prime is an m by m matrix. So since by 1, the trace of A prime is just equal to the trace of A. So when you have a matrix AB prime, you get the transpose of that. That is actually equal to BA prime. So the trace of AB prime is just equal to the trace of BA prime. That is by 1. But this time your matrix is AB prime. Also, the trace of AB is equal to the trace of BA. Here, this assumption is not used here. This is assumed that this AB here is conformable, no? Dapat conformable sila for it to be true. So that's why this given here is not carried over here because if we use this, AB here is no longer conformable. So this is in the assumption that AB will be conformable under general conditions. Also, in general, if we have, this is for two matrices. In general, if we have ABC conformable matrix, this is equal to CAB. So what we did here is we applied 3 on this, fixing your AB as one matrix. No? So you will have the trace of ABC is equal to the trace of CBA, or equal to in here, what is fixed is here is BC. So you have BC times A. But it's not equal to the trace of the permutations of the matrices. Okay, so let's recall now the moment generating function. So in your earlier lessons about moment generating function, you know that if your y is a random vector, so this is an n by 1 vector, y is an n by 1 vector, you know that the moment generating of your y is equal to, the general formula is just equal to the expected value of the exponential of y prime t, no? Or equivalently, y prime t can be expressed in matrix notation as the sum of yi ti. So if you will have a random matrix here, multivariate case, so instead now y sub I lang, you will have x xij, then the moment generating function of your random will be a double sum, no? So single sum for univariate, it will be a double sum for multivariate case. And to compensate with this double sum here, we will have a term, the trace. So it will be now, instead of using this y prime t, it will be the trace of x prime t. So that's the difference between the univariate case and the multivariate case. Now, take note, similarly in your univariate case, recall na the dimension of t here was the same as the dimension of y. The same thing here, the dimension of t here should be the same as the dimension of x. Okay, so some properties of your moment generating function. So here we do some variable transformation. This should be familiar to you. Okay, so if you have an x, which is n by p, no? And you have a to be any scalar. So if we do a transformation on x to be equal to scalar times x, we call that random matrix here now as w, then the moment generating function of your w is just equal to the moment generating function of your x, except that it will be at a t, no? So to solve that, by definition of moment generating function, which is equal to the expectation of the exponential of the trace of w prime t, and then you substitute this w prime by, okay, your w is ax, so your w prime here will be ax prime by definition of primes. This is a x prime a prime, but a is just a scalar, so it's just x prime a or a x prime. So w here can be equal, is just equal to ax prime. Okay, and then since a is just a scalar component here, you can have it with t, so that this form now will be the moment generating function of x at at. So this is quite easily done. Next, the next transformation on our x, again, x will be an element of r and p. So this is an n by p matrix. So be sure that it is conformable when you have axb. A is m by n, x is n by p, and b here is p by r. So it's conformable. Axb will be an m by r matrix here, and C should be also m by r. So that's why C here is an element of an n by r matrix. So from X, which is an n by p matrix, to Y, which is an m by r matrix now. Okay, this is your Y. The moment generating of your y will just be equal to the moment generating of your x at a prime t b prime times an expression which is just a constant actually, because c prime will be r by m, and t here will get the dimension of what? What's the dimension of t? What's the dimension of t?
M by R.
It will take the dimension of
Y.
y. Very good. Okay, so that's the dimension of t. So that is m by r. So it is conformable. And then if this is r by r matrix, and then you get the trace. So if you get the trace, that is just the sum of the entries of the C prime T, correct? And that is just a constant, no? So it's actually prime multiplied by a constant, no? The exponential of a constant is still a constant. Okay, so we don't have problems with the conformity of the matrices here. So let's proceed with how to prove this, of how to show this. So we start with what is the moment generating function of y. By definition, you can write it in this form. And let us look at this term here, y prime t. So y prime t, from here, so that is your y prime t will be equal to axb plus c prime times t, no? And this is equal to b prime x prime a prime plus c prime, and then multiply it by t, and you will have this one. Okay, so this implies that if we get the trace of y prime t, so that will be okay, the trace of a plus b. One property is that it is equal to the trace of a plus the trace of b. So you apply that property here, and you have that. And then again, using the property of a trace here, actually what is used here is the trace of AB is equal to the trace of BA, wherein this is taken as 1. This is taken as one vector here. So swapping it, you will have this 1 times B prime. Okay. The purpose of that is to isolate your X prime, because what you want is to get the moment generating of your X, and you want it in the form of the exponential of the trace of X prime something, no, in terms of T. So dapat maglahi si X prime. Okay. Kini. That's the technique there. So you will have X prime here as this one as your whole term there. Okay, so from sum, so this is your trace of y prime t, and then you get the exponential of it, but this is the sum. So if you get the exponential, apply the exponential here, and you get the exponential of this term, and you know that the exponential of a plus b will be equal to the exponential of a times the exponential of b. So that's why when you apply the exponential, you will have the exponential of a times the exponential of b. Are you still following?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Okay, so after that, if you scrutinize this, that is actually your, and then you get the exponential. So manaka-ani na term, magpaon dahil mo ang expectation ana, paon ang expectation ana. So if you get the expectation of that, you get the expectation of this term. So expectation of the product, but this is just a constant. If you scrutinize that, this is just an m by m matrix. Get the trace, that will be a constant. So the exponential of a constant, you can take it out from the expectation term. But this term here is actually a moment generating function of x at this term, a prime t prime. So we are done. Okay. Next, suppose we partition our x. Our x here is an n by p matrix such that x is partitioned as x1 and x2, but our x1 and x2 here are still matrices. x1 will have a dimension n by p1. So ibig sabihin, this is partitioning column wise, no? So kung naa kay original na x11, x12, and so on so forth, napaubos na siya. Di partition lang nimo kini. You still retains the n row, but P here will be subdivided as P1 and P2. So where P here will be equal to P1 plus P2. Okay, so what we are doing here is we get the marginal, no? The distribution of the marginals when we partition it column wise. T will have the dimension of your x. They have the same dimension, so that when we partition it into x, so T1 will have the same dimension as x1. So what is the result telling us? That the marginal moment generating function of x1 is just equal to the marginal, the moment generating function of x, wherein T2 is 0. Of course, similarly, the marginal distribution of x2 will be the marginal distribution of x, where T1 is 0. No? And another familiar result is that when x1 and x2 are independent, then, okay, this is an if and only if statement. Both ways applies. The moment generating function of your x can be expressed as the product of its marginal, no? So mx at t10 is actually your moment generating function at x1 at t1, and mx0 t2 is actually the moment generating function of x2 at t2. So for the proof, this is similar to what we have done in the univariate case, except that this time you will have a trace in your moment generating function. So I think you can follow through that. You first express, find this, the trace, which is just equal to this, because when the trace is just the sum of this, no? The trace of the sum of that. When you apply the trace, so equal na siya sa trace sa sum, which is just equal to the trace of T1 prime, T1 plus 0, which is just this term. And because of that, after getting the trace, get the exponential and get the expectation. So that is the moment generating function of x1 at t1. Okay. That's for B. So similarly, you can do this for mx2 at t2, no? Which is just equal to the moment generating of x at 0 t2. Okay. This proof, one direction, we assume that x1 and x2 are independent, and if this is independent, then the moment generating function of x2, which is by definition is this, and if you try to solve this, you will have this. So the trace of this cannot sum ani no, but applied the trace there. Nana siya trace diha. Kay kuha man nato ang trace. So that's the sum of that. Then get the expectation. And we see that since they are independent, so because of this assumption, this whole term here, after getting the expectation of the exponential of this term, we can express it as the product of the expectation, because we can only do that, this one. We can only do this if x and y are independent, but this is not in general equal, no? You should have assumption that x and y is independent. So after getting the expectation of this whole term, you cannot express it readily in this term, not until we have this assumption. Are you with me?
Yes, ma'am.
So because of that, if you look closely at these terms here, this is actually the moment generating at x1, no? And this is actually, by definition, the moment generating function at x2. So when x1 and x2 are independent, then the moment generating function of your x is just the product of the corresponding marginal moment generating function. So the other way around is you assume that it is independence, and you show that you assume that it is the product of this is equal to the product of its marginal moment generating function, and show that x1 and x2 are independent. So the converse is similar to what we have done in the univariate case, wherein we look at what is the form if we have the general moment generating function of x, and then compare it with this. Okay, so the converse is trivial. Next, the next transformation on x is when we get the transpose of x. So what will be the moment generating function of the transpose? Is just equal to the moment generating function of x, but this time instead at t, it will be at t prime. So by definition, if you have x, the moment generating function is the expectation of the exponential of the trace of x prime t, no? So if this is if that is x prime, so what will happen here, this is x prime prime. So which is just x. And since we are dealing with the trace and we have this result, so the trace, if your original matrix here is xt, and you get the prime of that, then that is t prime x prime, which is this one. So the trace of a, your a here is xt. You get the prime of that. The prime of that is t prime x prime, which is this one. And then you have to isolate x prime, no? Kaya in ani man ang forma imong gusto, x prime. But the x prime here is still in the second component or second term. So you have to apply this property that the trace of AB is equal to the trace of BA. Then you have x prime t prime. No? So karon na siya sa x prime. So it means that this is actually, by definition of moment generating function, the moment generating function of x at t prime. That's it. Questions so far? The questions? Okay, let's have a 5-minute break. We'll see each other at 8:46. I will still see my slide.
Yes, ma'am.
Okay, so let's continue. So now we will specifically study the normal distribution. So in this section, we will have the matrix normal distribution for a while. Okay, so remark 1.7 is worth noting that most computation in theoretical statistical derivation of density function uses the concept of moment generating function for these two particular reasons. No, most often MGF is easier than deriving distribution through its density functions or deriving statistical results using density functions. And the density function, if you recall, only exists or if it is non-singular, no? Or it is easier if the matrices, the sigma there is non-singular, but there are singular normal distributions that have MGF, but it has no density function. So if you recall, there was a result in chapter 3. Let me scan through it first. Actually, it's lemma 3.2. In general, your sigma or the covariance of a random vector or a random matrix is non-negative definite. But if your y has a continuous density function, then it's always the case that your covariance of your matrix or your vector or sigma is positive definite. So if walay density function, then your sigma is non-negative. It's always non-negative, and some of them will have no density function. So that's why we work with the moment generating function. Okay. So we start with a Z random matrix such that this Zij is independent and it is standard normal, no? Then recall the moment generating function of a standard normal will be equal to the joint density of this, the Zij's, but since they are independent, so it's just equal to the product, no? You get the product, but since they are independent, it's just equal to the sum of 1/2 t squared ij. So this is the moment generating function for standard normal. Okay? So wala pa mu and sigma squared. So now, this is your vector t. Tj is an n by 1 vector, implies that t prime t is equal to this. Vector multiplication will give you this, so that we are relating this in terms of the trace, no? So if we get the trace of t prime t, which is equal to the sum of t prime j, tj, or now, if we look at it component-wise, the entries, so you have this. This is for the first summation for the columns, and this is for the rows. So this is from J1 to P, and this is I from 1 to N. So the trace of T prime T will be double sum. So equivalently, that is substituted by the trace. So katong sa univariate case na single summation, no? Single summation raman ni sa univariate case. Sa multivariate case na double summation will be in terms of the trace. So that the density function of your Z, so moment generating function, it has a standard normal. This is the moment generating function of the standard normal, and this is the density function for a standard normal. So in terms sa multivariate term, you will have the trace, and then IID, so you will have n times p over 2, no? So double sum or double product n times p. So what will happen when we do transformation on Z? So recall na ang atong Z is standard normal, and then ang transformation on Z is Y equal to AZB plus mu. So if this is the dimensions of our matrices here and our mu matrix, this is M by R, similarly of what we have done earlier, katubitang from X, atong gi-transform sa Y, which is AXB plus C, no? So this time, C here will be mu. You still retain your A and B. And then we do similar transformations. So the first line here is by the result we have done earlier, that if we have a transformation from X to Y, where Y is AX plus B plus C, AXB plus C, then it is just equal to the moment generating function of X in our scenario, that is Z, at A prime T B prime, and times the exponential of mu prime T. Do you recall this result, no? Earlier.
Yes, ma'am.
And then we know that the Z here is normally distributed, no? So that if it is normally distributed, Z is normally distributed, actually standard normal, so that the moment generating function of a standard normal is equal to 1/2 trace of sa ganang naa diha, T prime T, no? Here. Yun. So T prime T, but your T here is actually what? A prime T B prime, no? So if you get T prime, that is B T prime A. So you will have B T prime A and then A prime T B prime. Correct?
Yes, ma'am.
Okay. And then what happened here? You use the property of a trace wherein you consider this okay. You consider this as one term here. So you will have T prime, A prime A prime T, B prime, and B. No, this is your B. So this is using this property of the trace. And then if you recall, in the univariate case, ang mugawas dito si ano lang, si sigma lang, wherein we let it to be B prime B, or dito sa notation nato sa univariate, it was A prime A, no? Sigma. But this time we will have an additional parameter, psi. So we will denote this by psi. A prime will be psi, and Zeo, nagklase lagi ko, dili magsaba. Okay, so this is A prime, and this will be sigma B prime B. So what you will have here is a term which is T prime psi T sigma. Okay, so this is what you will see if our y is, again, you know, when we have a z which is normal, any linear transformation, as long as addition lang na siya, the new transformed random variable is still normal, no? So y here will still be normal, and the moment generating function of a normal distribution will have exponential of, this time we will input, okay, sa ganitong sa univariate na case, kung naatay x na normal, di ba, exponential of mu prime t ra plus 1/2 man t prime sigma t, di ba? Correct?
Yes, ma'am.
Okay, so ana raman to sa univariate. Sa multivariate karon, you will have the trace of mu prime t. So mupuno tag trace din he, plus 1/2 times the trace of t, but this time we will have psi here and sigma instead of just sigma. So the sigma here is the variability among the elements of your vectors, but this time we will have matrix manggod. So one of them will take care of the rows correlation, and the other one will take care of the columns correlations, no, or associations. So I think I have some remark that will talk about psi and sigma. So let's have first this definition. So this is your dimension of your mu, your psi. So it is a square matrix. Sigma is also a square matrix. It's a non-negative definite matrix. And this is your dimension of your y. Y is a random matrix. So y has a matrix normal distribution with these parameters. So this time we will have three parameters, mu, psi, and sigma. That is, we write it in this manner. So if the moment generating function is given by this. So if the moment generating function is given by this, the moment generating function of a random matrix or a random vector is unique, no? So ibig sabihin, ma-identify nimo ang distribution sa isa ka random matrix by its moment generating function. So kung kana gyud, maora gyud na siya, unique na siya for a specific matrix. So if the moment generating function, this should be 2, is given by this, then your random matrix there, in this case y, will be normally distributed with these parameters. So some remarks: this distribution is not completely identified. So for a scalar greater than 0, y also has this distribution. It is normal with parameter mu. Psi is 1 over a psi and a sigma for the covariances among the columns. So you will see later that this will talk about the covariances among the columns or among the variables. And this will talk about the covariances among the rows, or the number of cases or the respondents. Now later, this component is usually taken to be just I, because usually when we have rows or cases at the start of the experiment, we usually make it a point that those rows there are independent, no? So for example, mga respondents, independent na siya, or person 1 is not related to person 2, and so on and so forth, no? So that's why in most statistical analysis, ang atong gina-consider is the correlations among the columns or among the variables or among the features, no? So ginaay ni nato kining correlations or relationships among the cases. Okay, so but this is not a problem in most applications, since the psi will be equal to I, which is a known matrix, or actually we make sure that the rows that we have or the cases that we have or the respondents that we have, as much as possible, are independent. So when psi is known, the distribution is completely identified. So usually this problem is eliminated at the start of the study. The researcher should make sure that the cases or the rows are independent, so that we can assume it to have the identity matrix. So for any non-negative definite matrix sigma, psi and sigma, there always exists a and B, such that we can write this. Therefore, for any mu, psi, and sigma of appropriate dimensions, or ibig sabihin, they are conformable matrices, such that psi and sigma are non-negative definite, there is a distribution having a moment generating function given by this into. So naagyo ni siya na moment generating function. Okay. So for the proof of theorem 1.5, what does theorem 1.5? Actually, we have solved similar proof of this in the univariate case. So if we have a y which is normally distributed with mean mu, psi, and sigma, this random matrix will have these components. Then the expected value of y will be mu ij, or actually your mu. The variance is of y is equal to psi. So variance talks about the same entries, no? I, and JJ. And covariance talks about different entries, ij and I prime, j prime. So this proof is by construction. So this is an assumption. If it is normal, then we can always construct y as a function of z, where z here is standard normal, no? And independent. And then we have this. So actually, kini na proof, murag bali ni siya sa nahitabo ani. Kini. Okay? So, before it was conceptualized, paani ni siya? Pabali ani, no? So, that's why they know. That is by construction. So, which implies you have this from here. You can always write it in this manner with respect to some matrix A and B. So naa kay elements diha sa imong A and B. And then if you get the expectation of this, so this part here will just be equal to 0 because z here is standard normal. So ang mabilin kini na lang. So this is true. And if you look at the covariance of the z's, it's either 1 or 0 lang, no? Because standard normal man siya. So if it is talking about itself, when k is equal to k prime and s is equal to s prime, then the covariance is 1. Kay standard normal identity man ang iyang variance. Otherwise, it's 0. And then with respect to the other components, it is equal to psi and j. By definition, kay ang ato ang pag-define manggod sa ato ang this is just equal to 0, 1, no? Because it is talking about the same thing. Man ang atong pag-define sa ato ang psi is AA prime. And B is B prime B. So this is AA prime. This is B prime B. So it's in terms of psi and sigma. You have psi and sigma there. So actually, pabali lang ni siya sa atong gihimo ganina. No? So this is a proof by construction. So remark, it helps to think that the psi, ni akong giingon, it will represent the covariance between the rows, no? And sigma will be representing the covariance between the columns of y. So usually for classical statistical methods, we usually assume that the cases kanang the row, respondents 1, respondents 2, respondents 3, or row 1, row 2 are independent. So most of the...
Yung panchang.
Lagi na binigyan.
Okay, so please mute, no? Or unless you have question. Do you have question?
No, ma'am.
Okay. So the psi will be representing the covariances among the rows, but usually we assume that to be equal to I as long as it satisfies, unless we are doing paired observation, no? Where there is some connections between the cases. Say before and after. You are getting weights before and weights after. Of course, the weight after is usually dependent on the weights before. So in general, for that kind of scenario, naatay psi, no? But if the cases are, or the rows there are usually independent, at the start of the study, then we can always assume psi to be equal to I. So therefore, the theorem that we have earlier states that covariances between two elements Yij and Yi prime J prime is just the covariance between rows I and rows I prime multiplied by the covariance of columns J and J prime. So that is what is meant by covariance. Okay. So this is actually also similar to chapters 3 result in the univariate case. These are some properties of the matrix normal distribution. So if we have X to be normally distributed with parameter mu, psi, and sigma, and if in particular, this R here is equal to 1, so you will have an M by R, M by 1. It will just be a vector. So, and sigma is just a scalar, sigma squared. Then your X will be normally distributed, still normally distributed. So kung N, M, 1, when R is 1, pwede ra nato tangtangon ng 1 din ha. And we just retain M here. And it will have only two parameters, mu and sigma squared psi. But then again, this psi, if you recall, sa ato ang univariate case, na atay normally distributed with mean mu and sigma squared I. Do you remember this?
Yes,
Diba
ma'am.
mauman ang usual na assumption nato, no? You have a random vector normal mu sigma squared I, no? Because you usually have the covariances among the rows to be equal, will just be equal to I. Okay? So when R is equal to 1, it narrows down to our usual univariate case. If we have a scalar A multiplied to, this is the assumption, no? The X is normally distributed with 3 parameters. So if it is pre-multiplied by A, your mu is pre-multiplied by A, psi is A squared psi, and sigma. Or if you want to put A square in sigma, so pwede po na siya normally distributed with A mu psi, and then A squared sigma. So the constant will be among the columns. And then if you get the transpose of this, still normally distributed, but mabali po ang imuhang dimension because the dimension of X is M by R. When it is X prime, it is already R by M. And the sigma and the psi will be interchanged, no? Because the rows here will become the columns, and the columns here will become the rows. Okay, and another result is D. So if you do a transformation on X by pre-multiplying it by C and post-multiplying it by D and add it by a matrix E. So this is the transformation. So X here to Y, say your Y is CXD plus E. Then CXD plus E will be still normally distributed, but the parameter changes to this form. So the mean will be C mu D plus E. The covariance for the rows will be C psi C prime, and the covariance for the columns will be D prime sigma D. And another result is if partitioning your matrix X mu, your sigma will be partitioned in this manner. This is talking about your variances. Still, this is just variances among 1, 1. So this is the dimension of your x1 and mu1. Then you have two marginals distribution. It is still normal, but the parameters is equal to this. So the psi retains its covariance value. And if the psi is not equal to 0, then x1 and x2 are independent if and only if the off-diagonal components of your sigma matrix here of diagonal are equal to 0. So if that is equal to 0, then x and y are independent. And next, if sigma 2 is positive definite, then we are assured of its existence of the inverse. Then the conditional distribution of x1 given x2 is just still normally distributed. Actually, we have solved this in the univariate case. The mean is equal to this. You have psi here, and the variance is equal to this. The covariance between the columns. So the usefulness of this is we can easily get the conditional distribution, the parameters of the conditional distribution. That is, this is the mean, no? So you can just look at the mean vectors and the covariance matrix to solve for the distribution or the parameters of x1 given x2. Okay. So for the proof, so I think you can follow through it. No? So moment generating function of x, you know x here is normally distributed, so it has this moment generating function. But this is just a scalar, so you can put it before here. The target here is to have this form here. Sa tong form na to, it is equal to the trace of mu prime t plus 1/2 ano siya, trace of t prime man na akadiha na component t. So kuhaon man nimo, no? So with it has a mean mu and sigma squared psi. So my question is, why can we remove trace from here to here? So dapat kini nakasulat din siya as 1/2 para parehag forma sigma squared psi t para makuha ni siya. So this is my question. Why can we remove trace there? Anybody?
Scalar. Scalar.
What's the dimension of
M by 1.
mu prime t? What's the dimension of that? What's the dimension of mu prime t? Anybody?
1 by 1.
It's but 1 by 1, no? So you know that the dimension is originally m by r, but then again, we let r to be equal to 1. So the transpose will be 1 by m, and t is m by 1. So this is just 1 by 1. So that if you get the trace of a 1 by 1 matrix, it's itself. Are you with me?
Yes.
Okay, so that's why you can remove the trace there. But this one should be written in this manner para makuha ni natong sigma squared. Just correct your notes. Okay. Okay, next. This is similar. This is should be familiar to you. You know that when we do a transformation on x as 80, it is just equal to the moment generating function of x at 80, no? But you know that x is normally distributed, so the moment generating function of a normal distribution is given by this, but at 80. So this is your mu t, there will be mu prime t, there should be mu prime 80. And then this is 80 t prime sigma t, there should be equal to this. And then a is scalar. So the a prime here and the a can be written as a squared. So you will have psi and sigma here. So mo na ang imuhang a squared psi and then sigma for your parameter. So this is equivalent to the moment generating function wherein your mu here is equal to a mu, no? And then a psi and sigma. Next, for the transpose, we have this result that the moment generating function of the transpose at t is equal to the moment generating of x at t prime. So here will be mu prime t, but ang ato ang t din here will be t prime. And then t psi, t prime psi, t prime at t. Ang itsura is t prime psi, t sigma. Pero ang atong mga t diha is t prime. So t prime prime psi, t prime sigma. Okay, so by property of trace, the trace of a is just equal to the trace of a prime. So ibig sabihin mu prime t prime, kuhaonin mo ang prime, will be t mu. So that is t mu. And here, the trace of AB is equal to the trace of BA. So this is true. And then the t prime prime is just t. This is t prime. So porma na siya. Kini siya dapat mo porma ta og unsa. Pormahon ni nato as mu prime t. So but that is equivalent to mu prime 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 t. So ang imuhang parameter din is mu prime. And then kini siya dapat mo porma ka og t prime psi t sigma. Man t prime. So pero trace man, so what you do is kini gyapon a b b a, so you will have T prime sigma and then T psi. So, mo na siya, forma na siya T prime. So, ang imuhang parameter ng karon will be sigma and psi. Question, do you understand? Do you still follow?
Yes, excuse me, ma'am.
Yes.
Mu prime siya, ma'am. Dili na siya mu.
Mu prime.
Ah,
Kini. Let me check. Basin. Let me check ha. Chapter 17. It should be mu prime, no? The proof is correct. Pero ang dinhi kulang. This should be mu prime. Okay, ang x nimo mu, pero prime mu prime. And then dinhi sa notes, just correct your notes. Dinhi siya dapat mu prime. Pero sa atong proof, correct man atong proof, no? It should be mu prime kay ang itsura nimo mao ni siya. Pero gusto nato ang itsura na exponential of the trace of mu prime t. Mao man na siya. Plus 1/2 t prime psi t sigma. Mao man ni ang moment generating function sa normal. So para mu prime na siya, isulat nimo og mu prime prime t. So ibig sabihin ang parameter nimo ani mu. No? Man kini kay t prime man dinhi kay kato pa man siya. T pa man siya. So i-swapping ni natong duwa. Kay trace man na. So t prime sigma t psi. So kini t prime na. So sigma na ang iyahang para dinhi. Sigma man psi na ang iyahang para dinhi. Okay? We always look at the form of the moment generating function. Here. Ini. Inani gid ang forma sa ano. So dapat naka mu prime ka diha. T prime ni dinhi, no? So para maitsura na siya. So mu prime. So ang imong parameter din is mu prime. So this should be mu prime. Okay?
okay, ma'am.
Sa notes nag-print?
Yes, ma'am.
Yes, ma'am.
O i-correct lang diha sa notes, no? It should be mu prime. Appeal tong sa taas.
Correct naman siya, ma'am, sa notes, ma'am.
Correct siya sa notes.
Opo,
Previous.
ma'am.
Ano ka ni na wala na reflect din sa ako. Anyway. Okay. Basin pag build na ako ani kay namang gukoy gi pang add din he. Just check it with your notes, no? Okay, edit ko sa akong notes. Kini akong gina-present. Ang akong gi-edit ni basin pag build na ako. dili niya mabasa ang slash P. Anyway. Here, what we are doing here is we transform our x into CXD plus E. So by the earlier result, you can, if it is equal to CXD plus E, we can write it as the moment generating function of x at C prime TD times the exponential of trade E prime T. And then you know that x here is normally distributed, so it must have this moment generating formula. And then what you do here is to make it in the form katong mu prime t, trace of mu prime t plus 1/2 trace of t prime mansay, maitsura siya na t and sigma, no? So imo na nang i-transform. So mu prime na naman siya mu prime. So murag okay na ni siya at mu prime ang imong t dapat malahi kini. So unsaon na nimo na malahi siya. So what you do kay trace man ni, so imo ning i-swap. So mahimo na siyang d prime. Okay, d prime mu hat C prime D, no? And then kay dapat mu prime D man, so dapat usa ka component lang siya na naka-prime. But D prime mu prime C prime is C mu D prime. Okay? So ibig sabihin ang ato ang parameter ani is C mu D. So mao ni ato ang parameter C mu D man later na pay plus E. Okay, ang atong gikuha ni kini pa man. Trace of mu prime C prime D man kini isulod ni ato later din para usak ka exponential raman to. Okay? So mao na siya na anay plus E man kini siya pormahon nato as T prime psi T ug sigma with the C. So kini siya magpabili ni siyang T prime ang T. So ang imong psi is C psi C prime man ang imong sigma is D prime sigma D. No? Kana siya. So kung tawagon na nato psi star o sigma star, mo ni ato ang psi star o sigma star. So psi star or psi will be C psi C star C prime, and then sigma will be D prime sigma D. Okay? Questions?
Wala naman.
Okay, ma-follow ra, no? Okay, actually, you are familiar with this, except that nagpuno lang tag trace, no? Sa ato ang moment generating function. Here, sa tong letter E, what do we want for letter E? Letter E, we want the marginal distribution of x1 and x2 if we will partition it. This is letter E. So we partition x in this manner. That is your different partition. Okay. So T here is also partitioned. And suppose T here, T2 here is just 0. So kay ang atong gusto si x1 man. So we look at the value of mu hat t. So if we multiply that, you have this. And get the trace of that. So that is equal to the trace of mu 1 prime t1 plus 0. So mabilin si trace mu prime 1 lang t1. And also we look at this term. Kay mao man ni ang katong 1/2 trace of t prime psi t sigma. So unsa man ni itsura ana. So we just multiply t prime psi t man sigma, and you will have this, and then you get the trace of that. So trace sum of this diagonal. So trace will be equal to that. So that the marginal MGF at x1 equal to this, and then you substitute mu hat t, but our mu hat t here, mu hat t will be equal to the trace of mu hat t will be equal to the trace of mu prime 1 t1, and the trace of t prime psi t sigma is actually this one. So you substitute it there. But looking at it, if you scrutinize on it, this is actually a moment generating function of a normal distribution with a mean equal to mu 1 and and covariance of psi and sigma 1, 1. So similarly, the marginal MGF of x2 will have the parameters mu2, psi, and sigma 2, 2. Okay. Next, this is a very important result, especially when we want to know whether x and y are independent. So we just look at the off-diagonal entries of your sigma or the covariance matrix of sigma. So in this direction, we suppose that this is true, and we show that x1 and x2 are independent. So if we assume that sigma 1 to is 0, your sigma matrix will be written in this manner. And then you try to find t prime psi t sigma. So t prime is actually t1 prime, t2 prime. Finish siya. So if you multiply that, so you have this, and then you simplify t prime psi, which is equal to this, so that if we have this as a whole, you have this. And then you get the trace. So it's just the sum of the trace of this and the trace of this. So you have this. So the trace of this will be equal to the sum of that. And then you also look at your mu prime t. So you always look back at this definition, no? that the moment generating function will be the exponential for a normal, no? The trace of mu hat t plus 1/2 the trace of t prime psi t sigma. So, kuhaonin mo, kuhaon ang trace, kuhaonin mo, kuha ang trace. So, ang trace, kini siya na part, mauna na siya. Kaya na, kini na part, mauna siya, kuhaonin mo ang trace, sum na nimo with respect sa trace nila. So, this is the trace of. Kana. So, i-substitute na dayon nimo na siya ani. Kaya mao man ni ang moment generating function yun. So, substitute it here. Mao ni ang trace of mu hat t. Mao ni ang trace sa t prime psi t. But then again, this is the exponential of the sum. So you can always write it in this manner. So it means that you have, if you scrutinize this, this is actually the marginal moment generating function. So since you have written it as a product, okay, the moment generating function of x as a product of the marginals, then x1 and x2 are independent. So next, the other way around, paingon dito, you assume that they are independent. You have to show that sigma 1, 2 is 0. So to do this, we look at the covariance value of your values here, but that is just equal to 0. No? Because x and y here are independent. So, 0 na siya. This term here will be, this is what the covariances among the columns, no? And since they are independent, partition sa columns man ni siya. So that will just be equal to 0. So this implies that sigma 1, 2 is 0. Okay. Next. This time, to prove this is by construction. So this proof is similar to what we have done in the univariate case. So ato tong define, multiply by this matrix here. So I will not discuss so much on this because you are familiar. Tanawa to ninyong univariate case. Maura the same flow lang except that it will be in matrix form na. Okay? So the same flow ang proof. So just study on this and compare it with the univariate case. Parehara na sila og flow sa proof. Okay? So before I will discuss theorem 17.3, let us have again another 10-minute break, no? So ganina niyo, ano man tag 8:40, karon 9:40 na. So 10-minute break, we will be back at 10 hours charge. Okay. So am I clear? Slide okay?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, so let's continue. So now we will have theorem 17.3. And here we assume that X is normally distributed with mean mu. So this time we will let our psi to be equal to I. This is on the assumption that the rows or the cases now will be just independent and there is no relationship or variability within them, no? So it's just independent. Note that this is an n by p matrix. So the x1s here is not a single value, but it is a vector. It is 1 by p. So this is 1 by p, no? Are you with me? And then this is also 1 by p. So there are n of them. So that is n by p. Okay? So this is also a vector of mu's. Ibig sabihin, kada isa sa x11, x12 to x1p has its corresponding mu's. So mu 11. So muna mu prime I ang x prime. Okay? Kada isa sa ilaha na ay iyahang kaugalingong mean which is mu1. So si kini siya constant mean siya pero mu1, no? So each of the xi's here are independent, and so kung x prime I here anong ana will be still normally distributed. So p by 1 man siya. So mo nang gi-prime kay ang katong papi din patindog. So that's why it's prime. Okay, so what do we want to see here? We want to prove here that if we have the x here are normally distributed, then each of the xi's there are independent and it is normally distributed. So again, the t for the moment generating function takes the dimension of your x. And then, so moment generating man na to, pangitaon ni nato. So recall, pag moment generating function gani, so multivariate, trace mu hat mu prime t plus 1/2 trace of t prime psi, pero I na lang atong psi, t, and then sigma. So mo boil down ni siya og t prime psi t lang, no? Kaya pwede na nimo ibutang in between. Okay. So we look at this. We find the trace. So from here, this is how we write our mu prime t. So we have this trace of a plus b is just equal to the sum of the traces. So you can interchange the summation and the trace. And then using this this result, so unsa na itabuan ni? Unsa may mu I prime ti, kuhanin mo ang prime. So that is T prime, Ti prime, then mu I, no? And then iswap nimo. So you will have mu I and Ti prime. And then gusto nimo na mu prime. So you will have mu prime I prime, then T prime. Okay? Then pangitao na po nimo si T prime T, which is equal to this. So katong kini siya kay I naman eh. Tapos ang balik sa saktong itsura. So kining dinhi will be T prime T sigma kay I na naman to diha. Okay? So this is equal to that. Kuhaon mo ang trace. Use properties of trace and summations. So ang imong gusto, may itsura siya T prime sigma T. Ano ni ang tuyo niya, no? Pero para maitsura ng T, dapat ang ato ang T prime. T prime I. So T prime I ni siya. So you are given that X is normally distributed. So this is the moment generating when it is normally distributed. And then that is equal to this. We obtain this, substitute it here. And then since this is exponential of the sum, just equal to the product, diba? E to the sum, EA, EB, no? So the product of the exponentials. And then, if you scrutinize the dimension of these two, it's just 1 by 1, so that trace here can be removed. So this remains to be, this is simplified in this manner. But if you look at this, what do you see here? This is a moment generating function, no? Of a normal distribution. So this is the moment generating function of what? Since this is mu I prime, so this is the moment generating function of xi prime. At, okay, dapat mu prime t raman na siya. So at t prime I, no? Morning t prime I ang t. So since that is the moment generating function of a normal, so it means that your xi prime here is still also normally distributed, and the parameters will be mu I prime and sigma. So that is what we want. Okay, so questions? So what we are looking at here is the distribution of our xi's, each of the xi inside your random matrix X. So it's still normally distributed. So for as long as the whole matrix is normal, each of the components is also normal. Do you follow?
Yes, ma'am.
So partition nimo ba na kung ang tibuok nimo matrix na kay mga normally distributed na as a whole. So it follows that kada component ana is also normally distributed. So tinuod ba kung kada isa normally distributed, kung iuban nimo sila normally distributed? Yes or no? Inani ako pangutana, di ba? Kana na result, na kay tibuok X normally distributed. Ang giingon ana na result, kada isa ka component din kining prime kana diha. Ina naman to na itabo kay si xi prime man to. Are you with me?
Yes, ma'am.
X1 prime, si X2 prime. So, kada isa sa ilaha, normally distributed pod. No? So, ako pa ko tanayin, ani. Kung namoy mga variables na kay, say, height. Si height, imong individually, normally distributed. Man si weight. So, height, weight. Normally distributed po siya. Man si age. Normally distributed po siya si blood pressure sa mga tao. Normally distributed ba? So kung ako nang emerge sa isa, height, weight, age, BP, kung ako emerge na, kung kintanawin na ako tibuok matrix, normally distributed ba ni? Yes or no?
Try to lang.
Na mo stop recording yun si Surungon ani kay mulat man ko sa inyong answer. Kung bay manubag, dugay kayo na mag-recording ron.
Yes. Yes, ma'am. Lago na ako independent.
Ha?
Yes ko independent. Kaning per
No conditions, walay conditions. Basta kabalo lang ka normally. Kung ako nang emerge sa isa ka matrix, normally ba na?
Dili mo.
Lahi-lahi sila, ma'am, no?
Ang height normally, pag check name mo univariately, ang height normally, ang weight normally, ang age normally, ang BP normally. Emerge nimo sa usa ka matrix kay gusto ka mag principal component analysis, emerge na nimo tanan. So, pasabot ba ang tibuok matrix ana as a whole normally pod? Yes or no?
No, ma'am.
Si Dina,
No, po ako, ma'am.
warag kang Dina to natingog, no? No? Man si Cuenca pod, no? Nato'y nag-yes, si Damian ba to?
Yes, ma'am.
So, pila ba ni kabuok na din eh? Kompleto na siguro mo 9. Ang uban?
Yes po, ma'am.
Yes, si kinsa ganito? Si Rongon?
Feel ko
Kinsa
lang
to
ako.
nag- Inyo
Ako
wala?
ang sarap ng
Isa ha, mag-stop sharing sa ako. Kaya di ko kita, manggod kinsa gatingog. Si Sorongon to?
Yes, ma'am.
Sorongon, si Maaghop. Yes, pod. So, Sorongon, Maaghop, og si Damian, tulo. Ang kontra, si Cuenca, si Ganob, upat na sila yes. Uman si, ang no, si Dumagin, og si, isa tong, isa gani na no?
Cuenca, ma'am.
Ah, si Cuenca. Si no po si LJ.
Mag-change ko pa.
Tulo. Tulo si no. Upat. Tulo. Kulang pa man. Si ano? Si wala nito bag. No, si Manzanades. So, tulo sila man. No. Upat. Pito. Si Kali. Si Kali o si Maaghop na lang.
Yes ko, ma'am.
Yes, si Kali. So, 5 na sila. Si Maaghop na lang.
Ma'am, nag-yes ko, ma'am.
Yes. Oh, dagana yes, oy. Dagana mali, oy. Kay kung yes pa na, gi-if and only if na lang unta to nila. Di ba?
Yes, ma'am.
Tanawa ninyo ang ano. Kay kung yes pa na, gi-if and only if na lang unta ni Arnold.
Mm-mm.
Wala man niya gi-if and only if. So, ibig sabihin, Dili tanan cases na matinuod na. Okay?
Okay, ma'am.
Pakita na ninyo sa inyohang report ng application na, no, labi na sa assign sa principal component analysis o multivariate analysis, MANOVA o MANCOVA. That's not true. There are certain conditions where the other way around is true, but it's not always the case. Okay? Kaya kung kana pa ang case unta, kini na theorem kang Arnold, kini siya. If and only if na lang unta niya. One directional naman. Do you understand? So
Yes, ma'am.
sa nag-yes, kaya kung yes pa unta na, if and only if na ni Arnold. Okay? So it's not true always, no? So ibig sabihin, particular to general is not true, but if it's general, then particular is true. So that is itawag ani ana Damian sa general to particular man, particular to general, empirical, unsa na ano term gani? What na po?
Universal to extension.
O kini siya kay general to particular ni siya. So empirical o unsa ganito, inferential ang isa. Ang inferential is particular to general. So dili siya inferential ang dating. Ito na siya, general to particular. Unsa man ang general to particular? Empirical? Ay, anyway. Sige na. Basta wrong tong mga pila to kabuok, 5. Okay, so change that perception na although pwede na ibali pero na mga assumptions, na mga restrictions ibutang. Okay? So naman to yung nag-comment ganina na true siya sa tugiingon. Okay, pwede not true in all cases. Actually, ka-question siya, no? Oh, naalay particular case na true. Pero dili tanan. Pero wala man ko, nag-ingon man ko na walay restrictions. Tinuod ba? Dili na siya tinuod. Okay, kung tinuod, pag if and only if na to ni Arnold. Okay? Next. The next theorem. Okay, do you still hear me? And is my slide clear?
Yes, ma'am.
Yes, ma'am.
Okay, so the next theorem is the joint density function for multivariate normal distribution. So observe that this is m times r, no? M times r, no? And then psi is only for the rows and sigma is only for the columns. Okay? And then this is the density. Ang usual ninyo makita, di ba? 1/2 pi square root sigma, di ba? Sa univariate, 1/2 of x minus mu over sigma squared, di ba? Okay? So you will still have the 1/2 there. You have to add the trace for the matrix. And then this part here, x minus mu squared, sigma squared. The sigma squared there will have 2. The denominator man na. Note that kanang sigma diha mo na equivalent sa atong sigma lang, no? Sigma squared. Wala siya. Dili nato gina notation na squared, di ba? Variance na siya na without the square. Are you with me? So, mo nang ra na siya, sigma raised to the negative 1 kay naman na siya sa ubos. Manakay additional component na psi. Uman, in terms of matrix, kining x minus mu square will be in terms of primes, di ba? Okay? So, equivalent na siya tanan. And then, this sigma here will be sigma there. But it is, since we are talking about matrix, it will be in terms of the determinant. Okay? this is to assure us that the inverse exists. So dapat positive definite ni siya. Naagi ni siya dapat sa assumption na positive definite. Why? Because we are dealing with an inverse, the existence of an inverse. And then for the proof, medyo taas siya. So you just look at this proof. And then it uses some Jacobian transformation. But I will not discuss that. You just read on that. So there. So section 1 and 2 is done. So I think I will stop there. I will continue tomorrow for lecture notes 2.